Today I will discuss about digital parking control system. Um, so this project represents a block diagram for an automatic car parking system. A keypad sets the maximum number of cars, which is stored in a register entry and exit sensors update an up-down counter, tracking the current number of cars. A comparator checks this value against the maximum. If the count exceeds 12, the system displays full. Otherwise, it shows space available. Um, Here is I can calculate with my ID 12 cars using digits from ID determine that 4-bit counter is required for tracking. In this flow diagram, I start the system use a keypad to set the maximum parking capacity. A sensor checks if a car is entering or exiting. If it's an entry, the counter is incremented. If it's an exit, the counter is decremented. The system can update the car count. It compares the current car count with the maximum, 12 cars. If the count equals 12, the system displays full. If the count is less than 12, it brings space available. The process repeats continuously. In this 12, digit 12 is given as input the encoder by using the keypad. The input is then encoded using 16 to 4 encoder as the input is a 4-bit value. Here is the 4 registers are used to hold the binary value. It will be serial in and enroll out SIPO register. Uh, Here is the 4-bit SIPO register. Now a bit comparator then used to compare the value A and B. A will come from the register connected to the encoder and B will come from the registers connected to the counter. B will be the initially 0. Here is the 4-bit PIPO register in this slide 5. When the parking lot is full, the system needs to communicate this clearly. So we created states on display using a 555 timer in a modified monostable configuration. And here is the counter diagram. In digital parking control system, we will use 4-bit up-down counter for 2-directional counting. The system will increase the count when the car enters the parking lot and it will decrease the count when a car exits. The up-down up-on input from the exit sensor. Here is the down counter and here is the up counter. Up-down sequence for 4-bit binary counter. uh, it's the brain of the system, the 4-bit up-down counter. We designed it using JK flip-flops and decrementing. For example, one of the core logic expression is J1 is equal to Q naught and up plus not Q naught and down, which helps the counter decide whether the count up or increments as they leave. It decrements the counter's output is a 4-bit binary number, and although it can theoretically go up to 15, we limit it to 12 to avoid overflow and ensure safety. This binary count is what fits into the comparator for the parking status check. In the question number 2, here we use 7-segment display using two 555 timers where one show full and other show space available. To show the full, we can use a stable mode 555 timer, which duty cycle is 100% means counters on. and the show space available, we can use another stable mode, 555 timer, which duty cycle is 100 minus 3%, where p is equal to is my id number from a plus c plus d plus e plus f into 2. Designing a circuit to activate the 2 7 segment display using 2555 timer. Here, here is the 4 second timer. Here is the frequency is 10 hertz, and the display will be on for 56 ms. The display will be off for 44 ms. The capacitor of 250 microfarad is the best choice from the given capacitance of 50 microfarad, 250 microfarad, and for 470 microfarad. The capacitors provides resistors values easy to obtain and safe for the timer. It achieves the required 56% duty cycle on value means the desired frequency 10 Hz with on average timing of 56 ms on the 44 ms off. The 470 for low resistors drawing too much counter, and 50 microfarad is very high resistors. And in the question number 3, here is the state diagram. Okay, this page provides a state transition table and HDL-like logic equations for the timing controller. State transition table um, here maps current states PS2, PS1, and PS0 to next states NS2, NS1, and NS0, and outputs A and B. Example, when reset 1, the system initializes to 000. Otherwise, it cycles through states on 000 to 001 to 010 and 011. Here is the logic equations. Next stage logic. NS0 reset combinations of PS2, PS1, and PS0. Similar equations for NS1 and NS2 output logic, and A and B are derived from state with PS2 and PS1. Here is the Verilog code, Verilog HDL code, and partial code defines a module TLC, and partial code defines a module TLC with inputs clock, RST, and outputs A and B. Uses internal signals, P state, N state, and combinational logic for state transitions. In the question number 4, we have here is the limitations. Counter may support only a small number of cars due to limited bit width, and the system requires manual input of the maximum capacity using a keypad, which is prone to human cars. The system depends entirely on entry and exit sensors, so only failure or um, miscounting courses incorrect display status. Using 555 timer limits flexibility changes to blinking behavior on logic require modifying physical components. Modification. Use higher bit counters to support larger parking capacities. Set maximum capacity out automatically through memory or software to avoid manual errors. Replace static saver Segment displays with programmable LED or LCD panels for better communication. Replace 555 timers and logic gates with a programmable controller to increase flexibility and control logic. Impact. By using bigger counters, the system can manage a uh, larger number of parking spaces easily without error. Better sensors and smart control system reduce. Advanced displays like LCD LED can show more helpful messages, making it easier for drivers to understand parking availability. Using a microcontroller allows settings like blinking time, displays messages, or total capacity to be changed by just updating the program. No need to change any hardware. Thank you so much, sir.